Hey everyone, welcome back to chapter 0. We are learning today, or refreshing I guess, about solving systems of equations, and all of these are going to be linear equations. As a reminder, a system is when there are two or more equations with the same variables. So you have to solve for all the variables. If it's two equations, that will be two variables. If you're solving for three variables, you will need at least three equations to be able to solve that. If there was ever a case where you solve 4 or 5 or more variables, you have to have at least that many equations to be able to solve that system. So with these linear equations, you have three methods to solve them. The first method is graphing. This one is best if they're both in slope-intercept form. As a reminder, that is y equals mx plus b, or point-slope form. That is y minus y1 equals m times x minus x1. And that is where you just graph the lines and you find the point of intersection. It works well when there is an integer as the answer. However, graphing is not always best because a lot of times you'll have rational numbers as your answer, or fractions, in other words. So a lot of times also the questions will ask you to solve it algebraically. You're going to want to rely on substitution or elimination. If one of the equations or both of the equations already have x or y isolated, that means by itself, substitution is best. Or if there's a coefficient of 1 in either equation, so like if you have a 1x or a 1y, substitution is usually best. Here's the instructions for how to use substitution. We're going to go over that in an example, so I'm not going to go through that now. And then for elimination, as a reminder, this is best to use if the equations are in standard form. That's ax plus by equals c. Or if there are the same or opposite coefficients in the two equations. So for example, if one equation has 2x and the other equation has negative 2x in it, that would be perfect for elimination. Or if they have the same coefficients, so like if one equation has 4y and the other equation also has 4y, elimination is great to use in that case. Again, I'm not going to go through how to use it because we're going to get into an example. The first one is telling us to solve it using all three methods. So I'm going to go through graphing, elimination, and substitution, and then we'll talk about which one would have been best. In this problem, if we're trying to use the graphing method, we need to put them in slope-intercept form. This top equation and the bottom equation, we'll call them equation 1 and equation 2, are both already in standard form, the ax plus by equals c form. So we need to switch them to slope-intercept form by getting y isolated or by itself. We'll start with equation 1. In order to get y by itself, we're first going to move the 3x to the other side. We'll put it as the first term because we want it to be in the order mx plus b. And then we'll divide every term by negative 2 in order to get y by itself. The negatives will cancel out, so we have 3 halves x plus 3. That's the first equation. The other equation is a lot easier since these both have coefficients of 1. We just move the x to the other side. It's negative x minus 2. That's equation 2. I'm going to color code these. Equation 1 is going to be pink. Equation 2 is going to be blue. And then I'm going to go over to the side. In order to graph these, we need to identify the slope and the y-intercept. You always start with the y-intercept. Let's start with the pink equation. It has a y-intercept of 3, since that's in the place of b in slope-intercept form. So the y-intercept is 3. And then the slope is 3 halves. So with a slope of 3 halves, that's positive. That means you're going to be going, it should be increasing. You're going to go up 3 and right 2 and place a point. 2 points is enough to make a line. However, with solving systems of equations, you'll want to be really precise. So you'll want to follow that same pattern in the other direction as well. And we'll say that's enough for now. We can always come back and add extra points if we need to after we figure out where the other line lands. I'll highlight that to show that's our pink line. Next, move on to the blue line. It has a y-intercept of -2. So place a point on the y-axis on -2, and it has a slope of -1. -1 is the same thing as -1/1. So since it's a negative slope, it should be decreasing. It's going to go down 1, right 1. Again, 2 points is enough to make a line. However, you'll want to put more points on this line because you want to be precise and figure out where the two lines intersect. So notice that just shared that same point on the pink line. That's really good. That means we can solve this graphically, because when you're solving graphically, you're looking for the point where the two lines meet. These 2 points meet at this point, these two lines meet at this point. This is the point -2, 0. And that tells me that the solution to this system of equations is x equals -2, y equals 0. Now let's go back and solve it algebraically with substitution and elimination. For the substitution method, it's best to look for a variable that has a coefficient of 1. You'll notice in the second equation, both x and y have a coefficient of 1. So let's write down the second equation and solve for either variable. It doesn't matter which one because of the fact that they both have a coefficient of 1. We already know y is equal to -x minus 2, so let's just go ahead and get that y by itself again. And since that's coming from equation 2, I'll highlight it in blue. That's an equivalent form of equation 2. We have to take that and plug it into equation 1. So notice equation 1 is 3x minus 2y, but we know that y is equal to -x minus 2. So instead of 2y, I'm going to put 2 times the quantity -x minus 2 equals -6. So this is coming from equation 1, because normally equation 1 says 3x minus 2y equals -6, but instead of 3x minus 2y equals -6, we're plugging in -x minus 2 for y. That way, this equation only has one variable in it. It only has x, so we should be able to solve this using our linear methods. The first step would be to distribute. We would have 3x plus 2y plus 4 equals -6. Sorry, that should say plus 2x. I don't know where that y came from. Combine your like terms. 3x and 2x together make 5x. Get x by itself by subtracting 4 and dividing by 5. Notice we got the same answer as we did graphically. X equals -2. To solve for the other variable, I would look at what you already have isolated. We already know y is equal to -x minus 2. So if y is equal to -x minus 2, we know y is equal to negative times -2. We're plugging -2 in for x, minus 2. So we're taking what we just got and plugging it back into the other equation. You can plug it into either equation, but since y is already by itself here, it makes sense to plug it into this one. So we simplify that, y equals 2 minus 2, so y equals 0. Notice we got the same thing as we did graphically. X equals -2 and y equals 0. Finally, we'll use elimination as the last method. For the elimination method, you're going to want to get coefficients that are opposites. So I noticed first that both of these x and y have a coefficient of 1, like we already talked about in the second equation. So honestly, I could eliminate either x or y. It would be the same amount of work. I'm going to go ahead and eliminate y. So if the first equation has a coefficient of -2, I want my second equation to have a coefficient of +2. In order to get that to have a coefficient of +2, I need to multiply everything on both sides by 2. So when I multiply everything by 2, I get 2x plus 2y equals negative 4. Now that's opposite coefficients, 2y and negative 2y. So I'll bring over my other equation. Sometimes you have to multiply both equations. In this case, you only needed to multiply the second equation. Once you have opposite coefficients, you add the two equations together. 3x plus 2x makes 5x. Negative 2y plus positive 2y makes 0y, which is eliminated. And negative 6 plus 4 makes negative 10. Now we're back to the same equation that we had before. 5x equals negative 10. Divide both sides by 5. You get x equals negative 2. To solve for y, you go back to your original two equations. It's probably easiest to plug this into the second equation, but you can plug it into either one. We know x plus y equals negative 2. So that means negative 2 plus y equals negative 2. To solve that, you're going to add 2 on both sides. Negative 2 plus 2 gives me 0 for the y value. Again, we got the same answer with the other method, elimination. Taking a look at all three of these methods next to each other, I would say probably elimination was the least amount of work, but you could argue substitution on this one as well, since the second equation had coefficients of 1 on both x and y. It wasn't difficult to get the y by itself and plug it into the other equation. Substitution or elimination would have been the best methods for this problem. Now take a look at the next problem. We have to inspect it and decide which method is best. So if I'm looking at this, I notice that they're both in standard form, ax plus by equals c. That's leaning me towards elimination, but let's check the coefficients. Notice that these two are completely different coefficients. However, for the y, I see a coefficient of positive 3 and a coefficient of negative 1. That's not bad because they're already opposites. I have a positive and a negative, but they're just not the same value. So I need this to have a negative 3 on the second equation, and then I could eliminate the y. That's not going to be bad. So I'm going to go ahead and choose elimination would be the best, and say because they're both in standard form, along with the fact that the second equation has a coefficient of negative 1 for y. So I'll multiply everything in here by 3. Just going to bring over my top equation and then multiply my bottom equation all by 3. So this one's just going to stay. Whereas the second equation is going to become 15x minus 3y equals 42. Now that I have opposite coefficients for the y values, or for the y variables, I can add my two equations together. 2x plus 15x makes 17x. 3y plus negative 3y makes 0y, so that's eliminated. And 9 plus 42 makes 51. Divide both sides by 17, and you get x equals 3. Once you have one of the variables, you go back to your original two equations and plug it back in to either one to find the other variable. It would be easiest to plug this in to equation 2, 5x minus 1y equals 14, before you multiplied it by 3 to keep it smaller. Take the x equals 3, plug it in for the variable x. Simplify, 5 times 3 is 15. Subtract 14 on both sides. You get 1 minus y equals 0. Add y to both sides, you get y equals 1. So the final answer for this is x equals 3, y equals 1. Basically what it's saying is that if you plug in x is 3 and y is 1 into both of the equations, substitute a 1 for the y, a 3 for the x, it'll make both equations true. Next, we're going to work on some problems that have special solutions. So far, every problem we've done has been consistent and independent, meaning that the two lines have had different slopes and the lines intersect at one single point, So there's one solution to the system of equations. There's only one point, one value of x and one value of y that will make both equations true. However, sometimes, like if you have the same slope, same y-intercept for the two lines, they're the exact same equation in slope-intercept form, they have the exact same graph on the line, there are infinitely many solutions to this system of equations. Another case that can happen is that you have the same slope but different y-intercepts, therefore the lines are parallel, and they never meet on the graph, therefore there is no solution to this system of equations. Let's take a look at some examples. Here's one. Inspect the system of equations and state the solution. I notice that these two equations have opposite coefficients for x and opposite coefficients for y, but they have a different constant. I already know what's going to happen here, but let me show you exactly what this comes out to be if you don't recognize it right off the bat. If I try to use elimination here and add these two together, I get 0x, so x is eliminated, and I also get 0y, so the y is also eliminated. And if there's nothing on that side of the equal sign, that means I have 0 equals 38. This is a false statement, meaning that there is no solution. If I had put these two equations into slope-intercept form, I would have seen that they had the same slope but different y-intercepts. When two lines have the same slope and different y-intercepts, they're parallel lines which never meet, meaning that they have no solution. Now on the other one, you might notice that the second equation is the exact same as the first equation, just multiplied by 4. Even the constant is the same, just multiplied by 4. 5 times 4 is 20, 2 times 4 is 8, 12 times 4 is 48. Since these are the exact same equation, just in a different form, just multiplied by 4, that means they are the exact same line on a graph. When two equations are the same exact line on a graph, that means that there are infinite solutions. Let's say you didn't notice that that was just multiplied by 4. If you had tried to eliminate, let's say you're trying to eliminate the y, and that means you would want to get them opposite coefficients. In order to make that a -8, I would have to multiply everything in my top equation by -4, giving me -20x, -8y equals -48, which is the exact opposite of my second equation. So when I add those two equations together, I get 0 equals 0, a true statement, which is another way to get infinite solutions. So if you don't recognize it right off the bat, even when you go to try to solve it algebraically, you should either get false or true. False means no solution, true means infinite solutions. Next, I want you guys to try to solve a bunch of equations, systems, and I'm not going to tell you what method to use, but you have to pick what method is best and solve it that way. No matter what method you use, though, you should get the same solution. Here are the correct answers for A, D, E, and I guess you can see C on this page as well. So that's all of them. Pause the video and make sure you know how to do those. And last but not least, we are going to review solving systems of 3 equations that have 3 variables. We learned this in Algebra 2 last year, but as a reminder, the first step is to find what's going to be known as your working equation. So your working equation should have a coefficient of 1 somewhere in it. So I could either choose my first equation because it has a coefficient of 1 for x and z, or I could choose my second equation because a coefficient of -1 is just as good. I'm going to stick with the first. This will be my working equation. Whatever has the coefficient of 1, in this case I have two options, that's the variable I will eliminate from the other two equations. So I'm going to just choose to eliminate z, let's say. So this is my working equation, and I'm going to eliminate z. The reason why I chose z instead of x is because I did notice that these are already opposites. So I'm always going to start with my working equation. X minus 2y plus z equals 15. And then I get to either choose equation 2 to go with that or equation 3 to go with that. I'll work with equation 2 first. 2x plus 3y minus z equals 7. Remember, I'm trying to eliminate z. They're already opposites, so I can go ahead and add these two together. I get 3x plus 1y, 0z, so that's eliminated, equals 22. That's one of my new equations with two variables in it. Now I go back and write down my working equation again. X minus 2y plus z equals 15. But instead of writing it with equation 2 like I did the last time, now I'm going to write it down with equation 3. 4x plus 10y minus 5z equals negative 3. Remember, I'm trying to eliminate z. In this one, they don't just eliminate right off the bat. Sometimes you'll have to multiply your working equation by an integer. In this case, if I want to eliminate z, I need to multiply everything here by 5. Multiplying it all by 5, I get 5x minus 10y plus 5z equals 75. Bring over your other equation. And now I can add them together. I noticed also the y's are going to eliminate as well, but that's okay. So I have 9x equals 72. Let's go ahead and squish this together. It's 9x equals 72. Sometimes usually actually, this other equation will have the same variables as what you had before. So it would have had x and y in it. This just happened to eliminate y as well. But now we have two equations, 3x plus y equals 22 and 9x equals 72. This is our new system of equations. So I'm going to act like I wanted to solve 3x plus y equals 22 and 9x equals 72. This is my new system of equations. Now this is actually really easy to solve. Sometimes you might have to use substitution or elimination, but the reason why this one's so easy is because the second equation is actually already one variable. So I can go ahead and solve 9x equals 72 by dividing both sides by 9 and getting 8. So I know x equals 8. And then plugging that back into the other equation, I know that 3x plus y equals 22. So 3 times 8 plus y has to be equal to 22. Simplifying, I get 24 plus y equals 22. And subtracting 24 on both sides, I get y equals negative 2. Once you solve the system, the new system, you should have 2 of your answers out of 3. Once you have 2 of the answers out of 3, the final step is to go back to your working equation. You're going to keep going back to that working equation. We already know x is 8 and y is negative 2. The third step is to plug in 8 and negative 2 into the working equation. So what I've done is I've rewritten the working equation. I'm going to take my variables that I already know for x and y and plug them back in with the values 8 minus 2 times negative 2 plus z equals 15. Simplify, 8 plus 4 plus z equals 15. Combine your like terms. 8 and 4 together are 12, so 12 plus z equals 15. Subtracting 12 on both sides, I get z equals 3. So my final answer is x equals 8, y equals -2, z equals 3. You sometimes might see this written as an ordered triple in alphabetical order. So it just goes x, y, z, which would look like this. This might be another way to write that answer. So to review, you first pick the working equation. You eliminate one of the variables from the other two equations. So we eliminated z from both equation 2 and equation 3. Once we eliminate z from equation 2 and equation 3, we come up with a new system of equations. Solve that system of equations as step 2. Once you've solved that system of equations, the final step, step 3, is to plug those two answers back into the working equation to find the final answer. Go ahead and try this on your own with the practice problem, and then pause and make sure you got the answer correct. That wraps up the lesson about solving systems of equations. We've solved all systems of linear equations. We've solved systems of 2 equations and systems of 3 equations. If you need extra practice on that or have any questions, feel free to contact me. I'm happy to answer them for you, and keep practicing because you will get the hang of it. You guys got this. See you next time for the last lesson of chapter 0, which is still going to be systems, but they're not equations. They're going to be inequalities. I'll talk to you again soon. Bye.